Hi everybody, and welcome back to my lecture series on hardware for deep learning. I'm Dr. Adam Teman of EnICS Labs at Bar-Ilan University. We're in part 2, Convolutional Neural Networks, and this will be the second section of our lecture. So, in our first part, we discussed the introduction to CNNs, some basics, and we discussed how to calculate the size of a layer. And now we're going to go on to additional CNN components and to famous CNNs. So let's start discussing some additional components that we didn't discuss in the last part of the lecture. Okay, so the first component we're going to discuss is the pooling layer. Okay, so what we saw before is that if we take stride and we make it larger than 1, the standard 1, it's going to reduce the size of the activation maps. But it does skip over part of the inputs, and that means we may be losing some information. Instead, or in addition to using stride, we can use something called a pooling layer. A pooling layer is similar to a convolutional layer. It does some sort of sliding of a window over the input, but instead of doing a dot product at each place that it slides over, it's going to apply some sort of other function. So, for example, and also it's done to each channel separately. So, example, we're going to do a max pooling 2 by 2 over here. So we have some sort of input with values in this 4 by 4 input map. Okay, and we're going to do a max pooling of 2 by 2. So we start with the first placement of our window, and we're going to look for the max in here. That's what max pooling is, and we see that the max is 6. Okay, different types of pooling, for example, are average pooling. We could sum up these and do an average over them, but max is one of the very common ones. Now, we decided to do a stride of 2, depending on what our downsampling we want to do is. So with a stride of 2, we're going to jump over to this area, and we're going to look for the max. It comes out in 8. We're going to jump over to this area, the max is a 3, and jump over to this area, the max is a 4. So using a stride of 2 and a max pooling window of 2 by 2, we're going to get this 2 by 2 output, which just has the maximum of each of these areas we looked at. Again, it's very similar to convolution, except for the fact that we don't have weights, and we just apply a function. So we don't need to store additional weights for doing this, and the function is usually much easier to apply than a dot product. So pooling is a very common thing, and we'll see it in some of the examples that we have later on. It also doesn't necessarily lose as much information as doing a stride during convolutions. Another component that we'd like to discuss is batch normalization. Okay, so in general, in machine learning, we tend to normalize and standardize our data. What that means is that we want to move our inputs to where they all have the same kind of distribution and weight. We want to make them have a mean of 0 and a standard deviation of 1. We want to make everything run between 0 and 1. This is very important in many different things. For example, let's say we're looking at car accidents and we want to make a neural network that discusses them. So we may want to look at how many miles the car has driven, and that could be a very small number, like it maybe drove 1 mile, and it could be a big number like 1,000 miles or 100,000 miles. But we may want to look at the driver's age, which may be 18, and it may be 45 or something like that. So we see that these two numbers are very different, and they're in different scales. So what we usually do is we want to normalize things and standardize them, so they're all going to be running between 0 and 1, and they're going to have a similar type of distribution with a mean of 0 and a standard deviation of 1. And that's very common and done for most machine learning problems. So we take the input set and we run this normalization on it before we run it through our network. However, what has been found out in recent years is that it's worth doing it on the hidden layers as well. So inside our networks, which are very deep, we could have a certain type of an activation that's very large and a certain one that's very small, and they could cause a lot of disruption inside our network. Also, during training, it causes all kinds of crazy things with the gradient, and it means we may be chasing our tail trying to fix gradients all the time. So that's why batch normalization was introduced. And what it is it means we put in a layer somewhere inside our network, or we put in many of these layers, that will look at the mean and the standard deviation of our input set And when I say input set, I mean an entire batch. So we go over and we find the mean and the standard deviation of a certain channel in our batch, and we go and we normalize according to that. So we take our input, we subtract the mean, and we divide it by the standard deviation. We have some sort of a little epsilon here to avoid numerical problems, but we see that when we do that, it actually will disrupt the data, will disrupt the output in the end. So in order to not disrupt the output, we add two additional factors, this gamma over here and this beta over here. The gamma is like a weighting factor, and the beta is an offset type of a factor or a shift factor. There's a scale and a shift factor, and we learn these along with our weights, and they help make sure that when we change the batch, it actually still gives us a good output. Okay, so where do we do this? There's been a lot of discussion about that. It used to be done after activations, but now it's very common to put this between the convolutional layer and the activation layer. So we add this batch normalization. Again, it's one mean and variance and standard deviation per channel, and we stick it in between the convolution and the activation, and it's believed that it's key to getting faster training and higher accuracy on very deep neural networks. It's pretty much a standard now. There are other types of normalization that have been used before. First of all, again, you can just normalize the inputs. This is actually doing normalization inside the network itself. There are other types of normalization that have been used, but batch normalization, since it came out, has been become the de facto way of normalizing, and it's almost considered a must nowadays. The other thing I wanted to discuss was fully connected layers, and fully connected layers we've actually basically discussed before, because those are the neural networks we saw at the beginning, where we have a bunch of input neurons and a bunch of output neurons, and each one of them has a weight to each one of the others. But they're also important now, even though we're doing convolutions. So what exactly is a fully connected layer? Or it's actually just a certain type of convolutional layer where basically when we do this, we're doing a big dot product where the whole convolutional layer is going to give us a single output. So if we have a bunch of inputs and a bunch of outputs, the output feature maps are just going to be the size of 1, and the filters are going to be as large as the input maps. So basically we have our input, and we have our filter, and they're going to be exactly the same size. So H and W are going to be the same as R and S, and then we're going to dot product each one of these guys by each one of these guys, sum it all, and we're going to get one output. So this times this, plus this times this, plus this times this, and so forth, and that's going to give us, we're going to sum them all up, and we're going to get one output. So a fully connected layer with a single filter is going to give us a single output. The filter is going to be huge, and there is no reuse of the weights. So each of these weights is only going to be used once, because we don't have anywhere to slide to. This whole filter is going to be stuck onto this whole input. That's basically what a fully connected layer is doing, and it's basically a matrix multiplication. So just as an example of this, and this is when we discussed in the previous lecture about how we would do our linear classifier on like a CFAR10 type of a problem, we had a 32 by 32 by 3 input, and we had 10 output categories, and we wanted to find a single number for each of these output categories. So the first thing we were going to do is we're going to stretch the input map, the 32 by 32 by 3 input, into a vector of 3072 by 1, so 32 times 32 times 3072. So each of this is the first, each of these are the dimensions of, we're going to have 10 of these guys, or 32 of these, 32, okay, and then 3 of them. Anyway, so we stretch this whole matrix, or this whole tensor, into one vector, okay, and then what we're going to do is multiply it by a weight matrix. So each filter basically, again, is going to have to be the same size. So each filter is going to have to be 3072 weights, and that will provide us with one output. Since we want to have 10 output categories, we need 10 filters. Okay, so we need a weight matrix that is 10 times 3072. So we need 10 of these columns to multiply by, and that will give us each one of these guys will give us one activation. Okay, and we're going to have a total of 10 of them. Okay, so we do a dot product between our input and between each one of these weight vectors, each one of these fully connected filters, and that's going to give us, each one of them is going to give us one output. So those are fully connected layers. So how do we put it all together? We drive the input through convolutional layers, activation, pooling layers, normalization, and finally, or at least traditionally, we use a fully connected layer to provide the output scores. So let's take a look at this. So we have some sort of an input image, goes into a convolutional layer. Generally, what we can tell from observing different types of networks that have gone through, what the first layers do is they look at these low-level features. They find types of edges and types of kind of things that appear in many different in different images. As we go down the convolutional network, what happens usually is that the final layers, they look at specific things. So maybe in this type of a picture, it would look at these three little wiggles here, but that may only appear in this image or in several images. So those are called high-level features. It may have like actually a nose of a certain type of dog, maybe one of the filters that this looks at. This is all kind of guesswork or trying to explain things to ourselves. In general, there are these different types of filters that try to look at different things, and we don't exactly understand them. But looking at them, we do see these types of things, that the early ones are low-level features and the late ones are high-level features. So if we take this convolutional layer and kind of blow it up and look what's inside. So the first thing we have here are these convolutions where we take these filters and we slide them over the input feature map. Then we add some sort of a nonlinearity, such as a ReLU, that's an activation, and then we add some sort of a normalization. Again, as I said, commonly now the normalization is actually put in between the convolution and the nonlinearity. And then we can apply, if we want, a pooling layer. Normalization and pooling are not necessarily done in every layer. Convolutions and activations are done basically in every convolutional layer. So this could be the buildup of a certain convolutional layer, okay, as we'll see in a minute in the examples that we're going to show. Finally, usually we have a fully connected layer, and the fully connected layer is also followed by an activation. So looking at that, now we can go into some famous CNNs, and we can also understand what the sizes are and what all the components are. So as I promised you before, we're going to start with the first convolutional neural network, which was Linnet. One of the versions of Linnet is called Linnet 5. Okay, and it was a network for digit classification, looking at the EnICS dataset. If you remember, the EnICS dataset is handwritten digits, and they're all classified to be the digits 0 to 9. Okay, it had 2 convolutional layers, 2 pooling layers, and 2 fully connected layers. It used sigmoid as the activation. This is before ReLU was figured out. Had a total of 60,000 weights, 340,000 max, and as I mentioned before, it was used in ATMs to recognize digits on checks. Okay, so here we see the buildup, how it appeared in the article, and let's go and start to count what exactly we see here. Okay, so as we see, we have the input over here, which is a 32 by 32 by 1 image. It's a grayscale, so we just have one color for one channel depth for the input pixels. Okay. So in the first layer, what we're going to do is we're going to have a convolution. We have 6 5 by 5 filters. Okay. They have to have the same depth as the input, so they're going to be 5 by 5 by 1 filters. Okay. So 6 5 by 5 by 1 filters. That will give us 6 output maps of size 28 by 28. So we had 6 filters, and we get 6 output maps. Because we used 5 by 5 filters and we didn't use 0 padding, we get 28 by 28 output maps. Okay, how many weights in total is that? Well, we had 6 filters of size 5 by 5. Okay, that's going to give us 150, but we can't forget that we have to have a bias, so it's a total of 156 weights. What about the number of multiplications? So again, we have 28 by 28 pixel output maps, okay? And each of them was made, each of these pixels was made using 150 multiplications, right? And then another addition for the bias. Okay, so that's going to come out 122,000 multiply and accumulate operations. So that was this layer, and we get these 6 28 by 28 feature maps. And let's go to the next layer. So the next layer was a 2 by 2 average pooling. Okay, so the 2 by 2 average pooling, as I said, it doesn't need any weights. It just does this averaging function on each of the parts, and it's going to go and change our 28 by 28 inputs into 14 by 14 outputs. The average pooling is applied per channel, so we're going to have 6 outputs as well. Okay, the third layer in Linnet was, as you see, it's going to be a convolution of, there's going to be 16 filters, and the size of the filters are 5 by 5. They have to have the same channel depth as the input to the layer. The channel depth here was 6. There were 6 filters that were 14 by 14. Okay, so again, we want to figure out how many weights there are in this. So our filters are 5 by 5 with a channel depth of 6, and there are 16 of them. That comes out 2,416 weights. Okay, plus of course the 16, that includes the 16 biases. Okay, and we want to know how many max there are. So again, our output we saw here, it's going to be 10 by 10 due to the losses at the edges, and we're going to have 16 of the output. So 10 by 10 times 2,400 is going to be 151,000 multiply and accumulates on that layer. As you can see, we had bigger filters, bigger inputs and bigger filters, or bigger inputs, I wanted to say, and now we have smaller feature maps, but many more of them, many more channels. So the fourth layer is going to again be pooling, and this time we're going to pool and take the outputs from being 10 by 10, we're going to make them 5 by 5. Okay, and finally we're going to have a fully connected layer here with 120 neurons. Okay, so how do we figure out this 120 neurons? So our output feature maps, we had 5 by 5 times 16 outputs. Then that's the input to the fully connected layer. The output to the fully connected layer is 120, so we have to have 120 by this. That's the number of weights and multiplications we have to do. That turns out 48,000 weights. Okay, then another fully connected layer. So the input to this layer is 120, the output is 84, and so we have 120 times 84 weights. Okay, and that's 10,000. And finally, we have an output that's 10 categories, so we need another fully connected layer from 84 down to 10. Okay, and so there's going to be about 1,000 weights, and that gives us this total of 60,000 weights in Linnet 5. So that was just going over really slowly exactly how we compute the number of weights and the number of max in each layer and what kind of this real type of network was actually doing. But again, Linnet was a very simple thing that was run back in 1998 when computation was exponentially slower, and we didn't have these big data sets like ImageNet, and we didn't run on GPUs. Alixnet is the one that made the big breakthrough in 2012. And again, there were 3 reasons for the breakthrough. First of all, this exponential rise in computational ability due to Moore's law. The second thing was the use of GPUs, which were massively parallel, and it could train this huge amount of parallel data. And the third thing was the fact that ImageNet existed. So ImageNet, which is this data set with a lot of images that are all labeled, it provided the ability to train this thing really well. And it won the 2012 ImageNet challenge, and it had a 16.4% top 5 error. Okay, this is a much larger network than Linnet. It had 5 convolutional layers, 3 fully connected layers. It has a variety of what happens here. Sometimes it has different strides, different filter sizes along the way. Okay, it used 61 million weights, 724 million max. Okay, a total of 61 million. I have that written there twice. Okay, so as we see here, Alixnet starts with 96 filters that are 11 by 11 by 3. Okay, and that turns out to have 34,000 weights and 105 million max. Okay, from this layer, Alixnet actually does something. It breaks the filters into two channels, so two separate channels here. So we have 48 filters in each channel. There are a total of 256 filters. Half of them go on half of the input channels, half of them go on the other ones. It's a type of a parallelization it does, and it also mixes and matches them at some point here. Okay, and so that's a total of 307,000 weights and 224 million max. Okay, and then we keep on going with, and again, different sizes. Now we have 3x3 filters. There, instead of 48, we have 256 of them. So here we already have 885,000 weights and 150 million max. And we keep on going, 664,000 weights, 112 million max, 442,000 weights, and 75 million max. Okay, this brings us to the fully connected layers. So L6 is already a fully connected layer with 4,096 filters, and that comes out to be 38 million weights in max. And L7 is 17 million weights in max, and L8 is 4 million weights in max. Okay, so you see that these things are already huge. There are many millions of computations, and also what you can also see here is that the number of weights in the convolutional layers is relatively small because we do this weight sharing, even though they have a ton of computation. While there are a lot of weights in the fully connected layers. The fully connected layers are real expensive because we do no weight sharing. Each weight is used exactly once, but the computation is lower than in the convolutional layers. So that was Alixnet, but other famous examples that you'll hear about, and I just want to show some features that came out with them. VGG16 is one of them. So that came out in 2014 and had a 7.3 top 5 error rate. It had 13 convolutional layers and 3 fully connected layers. Okay, the feature that's really interesting here, it had these 5x5 filters. 5x5 filters need 25 weights, but instead of, in order to save some of this weight storage at the expense of a bit more computation, I believe, it used stacked 3x3 filters. So if we have two 3x3 filters, each one has 9 weights, so 2 of them is 18 weights. And let's see how that works. So we have an input image, and we take a 5x5 filter. This is what we want to do, and that needs 25 weights to make this 5x5 filter. So instead of running a 5x5 filter, we take a 3x3 filter, run it over this guy like this, right? As we saw before, we slide it across, and it reduces our 5x5 filter into an area that has of 3x3. Then we can take another 3x3 filter and put it on here, and we get one output. So we were able to take the single output that we were supposed to get from a 5x5 area. We got that single output over here, but instead of using a 5x5 filter, which is 25 weights, we used 2 3x3 filters, which is a total of 18 weights, and we saved a bunch of storage that way. Okay, so this is VGG, and you can see that it's already a much deeper network that goes down. GoogleNet is the winner of the 2014 ImageNet Challenge. It's also known as Inception, and the reason it's known as Inception, it uses these Inception layers. It has 57 layers, which is considered 21 layers. It depends how you count these things, and one fully connected layer at the end. Okay, it uses a total of 7 million weights and 1.43 gigamax. Okay, so I just want to look back here a second. Here we had 138 million weights, and we had 15.5 gigamax. And you see that it was actually beaten out by a network that was much smaller, only 7 million weights and 1.5 billion max. Still, it's a lot of weights and a lot of max, but it was able to beat out VGG with fewer operations and less storage. How did it do it? It uses these things called inception modules with 1x1 bottlenecks. Okay, and the reason that Google did this is they wanted to train this thing on one GPU. So let's see what this inception layer is. Okay, we have a previous layer over here, and we take this layer, and instead of running it through just one single filter, one single channel or route, what we have is we divide it into several parallel routes that it can go through. Okay. Another thing is that we take this previous layer and we run it through one-by-one convolutions. One-by-one convolutions are a strange thing, but it lets us change the number of channels and a one-by-one convolution basically just goes over and it helps us change the previous layer's number of channels, and we call it a bottleneck layer. So it can make things smaller to deal with them easier, and then we use like an expand layer, like a 3x3 convolution, and we get bigger again. So it reduces sizes and then expands sizes to enable to have fewer weights and more max, and somehow this type of inception layer, this thing that does things in parallel, it's able to learn and be trained very well, and it also fits onto less hardware. And so you see that this did all of these inception layers, all of these little points here, these are inception layers that are done along the way. They also have these auxiliary classifiers, different places where they sample in the middle of the network and use it to calculate loss and help with training. So the final example we're going to discuss is ResNet, and the reason we're going to discuss ResNet is it's the one that beat the human level accuracy. Okay, it was in 2015 and it already had a 3.57% error, which is less than about 5%, which is human level accuracy. Okay, this is a real deep one. Okay, different versions of it have different number of layers, but the one shown here is 49 convolutional layers and one fully connected layer. ResNet has versions that are 150 layers deep and so forth. Okay, there are a lot of weights, 25.5 million, does a lot of max, almost 4 billion. One of the things that's interesting that ResNet introduced was this thing called shortcut modules or skip connections. So what are those? Sometimes it seems that when you're training things, you don't actually want to use a certain one of these layers. One of these, it's so deep that sometimes you have one that you just wanted to do like an identity matrix. So these skip connections, they enable us to, instead of going through whatever filters we wanted to do, we can just go and bypass them. And again, these things, they somehow work. It's not that explicable how they work, but they do. There's some intuition. As I said, sometimes we just want to skip the entire convolutional layer here, and that's what this is kind of doing. But the bottom line is it was able to train it and work and get a real nice error rate, and now these are these different types of methodologies and things that we can use. So that's what I wanted to discuss in this lecture. And again, the main references here are from the C231N class at Stanford and Vivian Z's tutorials. And next week we'll start with some hardware, some actual hardware for neural networks.